While you are watching this, Tropical Storm Bertha is forming in the northeastern Gulf of Mexico. The National Hurricane Center issued storm surge watches today from the Alabama-Florida border to the mouth of the Mississippi River, with 3 to 5 inches of rain forecast along the Louisiana coastline to the end of the week. That storm was not supposed to exist. 6 weeks ago, NOAA declared an El Niño advisory, and the expectation was that this would be one of the quietest Atlantic hurricane seasons in years. El Niño produces wind shear that tears storms apart, but the weekly Nino 3.4 index, the single number scientists use to measure how much warmer the Central Pacific is running compared to normal, just hit plus 2.1 degrees Celsius. That is the super El Nino threshold, crossed in mid-July. That number matters more than the storm. Bertha is the second named storm of the 2026 Atlantic hurricane season, and forecasters expect it to remain relatively weak. But the reason it matters has nothing to do with the storm itself. It matters because of what is building underneath it. The ocean does not care about predictions, and plus 2.1 degrees is weeks ahead of the pace set by the 1997 event, which until now held the record for the strongest El Niño in modern history. This is the story of what is building in the Pacific Ocean as we speak, what it has already done to the weather across this country, and what every major forecasting model on Earth says is coming for the rest of 2026 and into 27. What those models are projecting and what they are not yet able to tell us are two very different conversations. Both of them matter. To understand why a warming patch of ocean on the other side of the planet can reshape the weather over your house, you need to understand one system that functions like the lungs of the global atmosphere. Under normal conditions, strong winds called trade winds blow steadily from east to west across the tropical Pacific, pushing warm surface water toward Australia and Southeast Asia. That steady push allows colder, nutrient-rich water to rise along the South American coast, a process called upwelling. The trade winds also drive a massive loop of rising and sinking air across the Pacific called the Walker Circulation, which determines where rain falls and where drought settles across much of the tropics and well beyond. Think of it as the atmosphere's default setting, the pattern that holds as long as the winds hold. During an El Niño event, those trade winds weaken. Sometimes they reverse entirely. When that happens, the warm water that normally piles up in the western Pacific sloshes eastward instead, spreading across the central and eastern Pacific in a massive pulse of heat that oceanographers track in real time using satellite measurements and deep ocean sensor arrays. That pulse, called the Kelvin wave, carries the warm water east and brings it to the surface. The one that surfaced in the eastern Pacific this summer was unusually large and unusually fast, which is exactly why NOAA declared an El Niño advisory back in June, weeks earlier than many forecasters had expected. The moment that warm water reaches the surface, it begins heating the air directly above it, disrupting the Walker circulation, shifting the jet stream, and reorganizing rainfall and drought patterns across the entire globe. The strength of that disruption depends almost entirely on how warm that surface water gets. A mild El Niño nudges the jet stream, a strong one shoves it. A super El Niño effectively rewires the atmospheric circulation for an entire season, sometimes longer, with consequences that echo for years after the ocean temperatures return to normal. And this is where the 2026 Pacific warming separates itself from everything in the modern record. The data that came in over the past 3 weeks changed the picture considerably. The International Research Institute for Climate and Society at Columbia University reported that the weekly Nino 3.4 index, centered on July the 15th, climbed to plus 2.1 degrees Celsius. That is a sharp acceleration from plus 1.55 degrees in June alone and plus 0.98 degrees averaged across April through June. The rate of warming is not just notable. Researchers writing in the Eurasia Review today described this event as developing faster than the 1997 El Niño, which until this year held the record for the fastest onset of a super El Niño event. But the raw index number is only part of what makes this significant. What the models are projecting for the peak is where this event enters territory no modern forecast has ever mapped. The GFDL laboratory at NOAA, one of the most respected climate modeling institutions in the world, ran their July predictions using a system called SPEAR. Every single one of their 30 ensemble members, all 30 independent simulations, projects this El Niño will reach at least competitive strength with the strongest events of the past century. Climate scientist Zeke Housefather, writing at the Climate Brink, compiled the full multi-model ensemble and found the consensus forecast projects a peak of roughly 3.6 degrees Celsius above average. To put that in context, the previous record holder, the 1997-98 Super El Niño, peaked at about 2.5 degrees using NOAA's adjusted relative index. 11 of the 14 models Housefather compiled show this event exceeding that record. The European Center for Medium-Range Weather Forecasts, the ECMWF, has gone further, suggesting that water temperatures could top 3 degrees Celsius above average as early as September before the event even reaches its expected peak later in the fall. NOAA gives El Niño a 97 to 99% chance of persisting and strengthening through the 2026 to 2027 Northern Hemisphere winter. That is not a hedge. That is about as close to certainty as seasonal climate forecasting gets. What none of these models can currently do is predict the specific timing, location, or intensity of individual weather events that a super El Niño will produce. That distinction matters enormously because the difference between a forecast that says California faces elevated flood risk this winter and a forecast that says a specific county will flood on a specific date is the difference between what climate science can deliver and what it cannot. To understand what that kind of peak could mean in practice, the 1997-98 event is the closest comparison, and its impacts reshaped how federal agencies prepare for El Niño winters entirely. That event produced catastrophic flooding across California from December through February. More than 7 inches of rain fell in parts of Orange County in a single day. Downtown Los Angeles received nearly 14 inches in February 1998 alone. Mudslides destroyed homes up and down the California coast. In the San Francisco Bay region, high winds and abnormally elevated sea levels combined with heavy rain to flood Highway 101 north of the Golden Gate Bridge under 4 feet of water. Across the United States, the 1997-98 El Niño winter killed 189 people, primarily from flooding and tornadoes, and caused an estimated $32 to $96 billion in global damage. A study published in Science estimated the event's ripple effects cost the global economy $5.7 trillion within 5 years. That was at a peak of 2.5 degrees. Current models project 3.6. But numbers from 1998 only tell part of the story, because those numbers landed on a planet with a lower baseline temperature, less moisture in the atmosphere, and considerably less population density in the regions that got hit hardest. What this El Niño is doing to the weather right now before it has even approached its peak is where the comparison to 1997 stops being useful and starts being misleading. The effects of the 2026 El Niño are not waiting for winter. They are already visible in the weather patterns that have defined this summer, even if most coverage has not connected those events back to the Pacific. And this connection between what is happening in the water and what is happening in the sky above your city is the part of the story that deserves considerably more attention than it has received. The extreme heat that shattered all-time temperature records in Billings, Montana at 111 degrees and Salt Lake City, Utah at 109 degrees on July the 12th arrived underneath a ridge of high pressure whose position and intensity were consistent with the atmospheric pattern El Niño produces. This week, heat indices across southern Illinois, western Kentucky, and southeast Missouri are reaching 116 degrees. Researchers at the European Weather Service Severe Weather Europe identified what they called a clear El Niño configuration in the atmosphere as early as June, with rising air over the Pacific and sinking air over the Indian Ocean confirming the circulation had already responded to the warming ocean below. That same pattern has fed the drought and wildfire conditions across Colorado. The Aspen Acres fire in Custer and Pueblo counties has burned more than 100,000 acres and destroyed over 850 structures, making it the 8th largest wildfire in Colorado history, with more than 1,600 personnel still fighting it. 4 firefighters have been killed across the Colorado Fire Complex this summer. 3 members of a helitack crew died in a burnover on the Snyder Fire on June the 27th. A helicopter pilot named Nicholas Dale, 56, from Sook, British Columbia, was killed when his aircraft went down at Silver Jack Reservoir while fighting the Gold Mountain Fire on July the 12th. Nationally, wildfires have burned more than 3.3 million acres so far in 2026, well above the seasonal average. The quiet Atlantic hurricane season was supposed to be the one piece of good news in this pattern. El Niño suppresses organized storm development through increased wind shear, and forecasters predicted exactly that. But today, Tropical Storm Bertha formed in the Gulf, and the paradox at the center of this entire story just arrived in real time. The air column over the continent does not care whether a system earns an official name. Rain does not need to be tropical to flood a river, and one of the defining features of a strong El Niño year is that while it suppresses organized hurricane development, it simultaneously loads the sky with moisture and repositions the jet stream in ways that produce catastrophic rainfall from systems that never appear on a tracking map. The Missouri flooding on July the 10th, where 12.25 inches of rain fell in hours and triggered 351 water rescues, did not come from a named tropical system. It came from a stalled front wringing out moisture the atmosphere had been holding since the heat dome arrived. India's nationwide monsoon rainfall through mid-July was running roughly 20% below its long-term average, consistent with El Niño's documented suppression of South Asian monsoon activity. The Eastern Pacific, where El Niño supercharges rather than suppresses storms, had already produced 5 named tropical storms by mid-July. That split, a quiet Atlantic with Bertha now forming, an active Pacific, a failing monsoon over India, intensifying drought across the American West, is not a collection of disconnected weather stories. It is one story. The same ocean warming that suppresses Atlantic hurricanes is the same warming that dries out India, that repositions the jet stream, and that sets the stage for the compounding disaster sequence the summer has already begun to produce. The question forecasters are now focused on is what happens when this El Niño reaches its projected peak later in the fall and into the winter. And the historical patterns from past El Niño winters are specific enough to warrant genuine preparation, even though the precise timing and severity of individual events remain beyond the reach of current models. During strong El Niño winters, the jet stream over the northern Pacific shifts southward, dragging a train of storms over the southern tier of the United States. California, Texas, and the Gulf Coast historically see elevated rainfall, and in 1997 to 98, that rainfall was devastating. California specifically faces the prospect of atmospheric river events amplified by El Niño conditions, pushing moisture directly into the state from the warm Pacific, potentially producing the kind of multi-day drenching events that overwhelmed drainage infrastructure and triggered mudslides across the coast during both the 1997 to 98 and 1982 to 83 Super El Niños. But the winter flood risk is not the only timeline that matters. The World Resources Institute has flagged potentially record-breaking forest fire activity in the Amazon during the second half of 2027, when the El Niño's legacy of reduced wet season rainfall leaves the following dry season even more fire-prone. Elevated fire risk is also expected across Southeast Asia, Australia, and Canada later this year and into 2027. The consequences of a super El Niño do not end when the ocean temperatures drop. They ripple forward, compounding through ecosystems and agricultural cycles for years after the event itself has passed. That lag is the part of this story that rarely makes headlines, because the damage arrives after the ocean has already cooled and the El Niño has officially ended. But the forests and the fields and the water tables do not reset on the same schedule the index does. And there's a broader number underneath all of this that deserves more attention than it has received. El Niño years are historically the warmest years on record, because the heat released from the Pacific adds directly to the warming trend already driven by greenhouse gas accumulation. The 2023 to 2024 El Niño, which was strong but not super, contributed to making 2023 and 2024 the hottest years in recorded history. A super El Niño in 2026, peaking into 2027, layered on top of a warming baseline already higher than during either of those years, is expected to push global average temperatures into territory no instrument has ever recorded. Wherever you happen to be watching this, the practical question is what changes for you? El Niño is a probability shifter. It does not predict specific events. It tilts the odds, making certain outcomes meaningfully more likely across certain regions for certain seasons, in ways that historical data allows scientists to map with genuine precision even when the specific timing of individual events remains unpredictable. The southern United States and California face elevated flood risk through the winter. Across the western interior, drought and fire conditions may not ease significantly even after temperatures cool. Agriculture is looking at a growing season shaped by compounding stress from heat, drought, and erratic rainfall patterns. And the global economy faces the same kind of cascading disruptions to food supply, energy demand, and disaster response budgets that the 1997 to 98 event produced at a lower peak intensity than what current models are projecting for this one. The preparation is the same regardless of whether this El Niño ultimately breaks the all-time record or merely approaches it. Know your flood risk before the rain starts, not after. If you live in a wildfire-prone area, maintain defensible space and have evacuation plans current. Pay attention to flash flood watches with the same seriousness you would give a hurricane warning. And do not mistake a season with only 2 named Atlantic storms for a safe weather year. The atmosphere is loaded. The question is where and when it unloads, not whether it will. Here is where this story stands as of today. The Nino 3.4 index has crossed the Super El Niño threshold weeks ahead of the 1997 pace. Every major model projects a peak that would make this the strongest El Niño in at least 155 years of reliable records. That warming is already reshaping weather across the planet, and it has not yet reached its projected peak. Behind every one of those ocean temperature readings is a firefighter in Colorado who will not come home, a family in Missouri pulled from rising water in the middle of the night, a farmer in India watching the monsoon that feeds a billion people arrive weeks late and inches short, and a Kelvin wave still pushing east through the Pacific, carrying heat that has not yet reached the surface, toward a peak that no living forecaster has ever had to model.